Hello friends, welcome to Mu Lessons. Today our topic is about the concept of self-inductance and mutual inductance. In the previous video we have learnt about electromagnetism, Faraday's law, Lenz's law and a lot of questions. So that has given you a clear idea about electromagnetism. This is a next part, we can say an extension of electromagnetism. First of all, let me review what is electromagnetism. Just simple. A wire carrying a current I causes an MMF. This produces a magnetic field. This MMF, magnetomotive force, has units of ampere, and for a single wire F is equal to I. In this case you can see a current carrying conductor, voltage source is applied, and in this case it develops a magnetic field. The direction of rotation of motion is given by the right hand screw rule. Now, the magnitude of the field is defined by the magnetic field strength, that is H. H is I net current by L, length of the magnetic circuit. For example, let us see one question. A straight wire carrying a current of 5 ampere, magnetic field strength H at a distance of 100 millimeter. So current is given, L is given. Now we have to calculate the magnetic circuit in the circular. For that, radius is given as 100 millimeter. So the path area is 2 pi r. The circumference is given as 2 pi r. It becomes 0.628, and hence H, that is the magnetic field strength, equals to I by L, and it comes up to be 7.96 ampere per meter. These are some simple questions regarding electromagnetism, self-inductance, mutual inductance, and calculating magnetic flux, magnetic field intensity, magnetic field, etc. The magnetic field produces a magnetic flux. This is a very common thing. It has the units of Weber. The strength of the flux at a particular position is measured in terms of magnetic flux density, B. This is a very important term. You should remember magnetic flux density, B. It has units of Tesla, means 1 Weber per meter square. B is given as mu into H. This is the relation between magnetic flux density and magnetic strength. B equals to permeability times the magnetic strength. This mu can be further written as mu 0 into mu r. Mu r is the relative permeability and mu 0 is the absolute permeability of the free space. Now, how can we increase the flux linked to the surface? You have listened, we use an iron core in a solenoid to increase the linkage of flux. It is similar to that. Adding a ferromagnetic ring around a wire will increase the flux. The more the flux linkage will occur, the more is the EMF induced, and the more is the magnetomotive force. So, if you consider this case, it is just a simple ring, and if you consider this case, it is surrounded by the ferromagnetic ring. So in this case the flux linkage will be more, and hence it is more effective than the previous one. When a current carrying conductor is formed, the magnetic field is concentrated. In this case, when you put a current carrying conductor in shape of a coil, the magnetic field becomes more concentrated, and for a coil of n turns, the force is current into number of turns, and the field strength is similarly IN by L. The magnetic flux produced is determined by the permeability of the material present. A ferromagnetic material will increase the flux. As said before, an iron rod is used in this case, and this increases the linkage of flux to this coil, and hence the permeability increases. Permeability is a very simple term. It is the intensity of which the linkage of magnetic flux takes place with the coil. Now, a simple term, that is reluctance. In the first video, that is in the DC circuit part, we have learned what is resistance, what is resistivity, what is resistive circuit. Resistance is a measure of how circuit opposes the flow of electricity, that is, the opposition to the flow of electrons is termed as resistance. What if there is an opposition to the flow of magnetic flux? The opposition to the flow of magnetic flux is termed as reluctance. and it is denoted as S. In the resistive circuits, R equals to V by I, and similar to that, reluctance equals to F, the magnetic force, by flux, that is phi, and its unit is ampere per Weber. Now, inductance. Inductance is term related to the inductors, in which the EMF or current is induced from one part of the coil to another part. A changing magnetic field induces an EMF, means it generates an EMF in any other connector within it. In the previous video, we have learned about this Faraday's law, Lenz's law. Again, I want to recall them. The magnitude of EMF induced in a circuit is proportional to the rate of change of magnetic flux. Means, as the rate of change of magnetic flux increases, the magnitude of the EMF also increases. And the direction to this EMF is given by the Lenz's law. That is, it tends to oppose the current that produces the change of flux, and hence the Lenz's law is given, the direction of the EMF produced by the Faraday's law. You can remember E equals to minus n d phi by dt. That minus was due to the Lenz's law, and d phi by dt was according to the Faraday's law. When a circuit forms a single loop, the EMF induced is given by the rate of change of flux. When the circuit contains many loops, it is just the sum of each of the loops. Therefore, in a coil having n loops, the induced voltage will be V equals to n d phi by dt, because n times means the n number of loops. This property is where EMF is induced and results in a change of magnetic flux. Now, let us come into the main topic, that is self-inductance. Inductance means to induce. Self-inductance, inducing something within itself. The changing of current in a wire causes a changing in magnetic field about it. This magnetic field induces an EMF within the conductor. Therefore, the current in the coil changes and induces an EMF in the coil. This process is known as self-inductance. It is given as V equals to L dL by dt, where L is the inductance of the coil. This is what we call self-inductance. Its unit is same as Henry. Self-inductance means, just in simple terms, something changing with itself, that is inducing itself, inducing the EMF with own, that is known as self-inductance. Suppose you take an inductor. The inductance of the coil depends on the dimension. Obviously, you know this L is given as mu0 a n square by L. This is a well-known formula. Inductance, self-inductance, mu0 a n square by L. This part depends upon the dimensions: area, number of turns, and length. The inductance is greatly increased. Now you can see this coil. It is just a solenoidal coil. Now how can we increase it, the inductance? Similar as before, if we use a ferromagnetic core or an iron core inside it, so that the magnetic flux linking to it will be maximum, in that case it will be maximum. The inductance is greatly increased through use of ferromagnetic core, and when you come to use a ferromagnetic core, we have mu0 into mu r. Similarly, energy stored. Whenever there is inductance, some energy is stored. That energy is given as half Li square. Now the next main topic is mutual inductance. Mutual means among two, within two things. Either it can be within two coils, two wires, two conductors, or anything. When one coil is linked with magnetically changing current, it will produce a changing magnetic field in the other coil, and hence it will induce a voltage in the other coil. This is known as mutual inductance. Mutual inductance given as V2 equals to M di by dt. This circuit induces a voltage V2 in another circuit. Then M is known as the mutual inductance between the circuits. Its unit is given as Henry, same as self-inductance. So we should keep in mind, in case of mutual inductance, two coils are involved, and in case of self-inductance, only one coil is involved with itself. Similar to this case, we have two solenoidal coils as an example for mutual inductance. When there is a magnetic field linking to this first coil, there is a change in magnetic field with the second coil, and hence it links with the other. This is known as mutual inductance. But you can see some of the flux linkages are very loose. Not all are connecting to each other. So in this case, how can you increase the inductance in this case? Simple. If we use a core, a ferromagnetic core, the net flux linking will increase. More the linkage of flux, more is the inductance, and hence we'll get larger inductance in this case. The fraction of magnetic field that is coupled is referred as coupling coefficient. Coupling is particularly important in transformers. About transformers we will study in the next videos. Coupling is the main part of transformer. The primary winding, secondary winding, both are coupled to a core, and whenever there is a potential voltage change in the primary side, the flux linkages occur with the second side, and in the second case, in the secondary side, we get the voltage. We will learn it afterwards. For the time being, coupling is a particularly important for transformers. It is a well-known example for this. You can see like here, AC voltage is wound around the primary side, and V2 is gained by inductance from the secondary side. There is a lot of linkage of flux within this core. This core is used in order to increase the linkage of flux to both primary side and secondary side. This is a very well-known formula, that is the transformation ratio. V2 by V1 equals to N2 by N1. Now let me tell you one example or an application of this inductance in sensors. Suppose, how can you use these sensors? This is going to be used in a proximity sensor. Basically, a coil is wound with a ferromagnetic core, and whenever this part comes in contact with a ferromagnetic plate, it induces current, and whenever it induces current, it acts as a sensor. So this is used in proximity detectors, the bomb squads. A ferromagnetic plate is coming close to the coil changes its inductance, allowing it to be sensed. This can be used in a linear sensor or a binary switch. So after so long, we can get a summary about this. Inductors store energy within a magnetic field. A wire carrying a current creates a magnetic field. But how can you increase that? By using a core. A changing magnetic field induces an electric voltage in any conductor within that field. If it induces within itself, that is known as self-inductance. If it induces to other nearby coils, then it is mutual inductance. And how can we increase that? Just by using a ferromagnetic core. That will increase the linkage of flux. Now, inductors can be made by coiling wire in air, but greater the inductance is produced if ferromagnetic materials are used. The energy of the inductor is given as half Li square. Example is transformer or proximity sensors. Now this is the analysis part. We will analyze how self-inductance and mutual inductance actually occur. In one coil, self-inductance obviously will occur in one coil. If you consider two coils, inductors, two solenoids have self-inductance plus the mutual inductance. Both are included in case of two coils. Let us consider first the first one coil. Potential is given, a circuit, there is a coil, magnetic field. In this case, only self-induced EMF is produced. So this is an example of self-inductance, and we can easily calculate the value of L as mu0 N A by L. Now suppose the magnitude of flux phi depends on the magnitude of the coil current and the number of turns. If we increase the number of turns, the flux linkage will increase, and if the number of turns is increased, we can increase the linkage of flux, and to increase the flux linkage more, we can use a ferromagnetic core. There is a simple derivation of self-inductance. The same figure you have seen below, seen above. V equals to N d phi by di into di by dt equals to L into di by dt. So it comes up to be L equals to N d phi by di. This is the formula. Now this picture shows you a figure of mutual inductance of between the two coils. Here is a coil number 2 having self-inductance L2, coil number 1 having self-inductance L1. So there is a linkage of flux among the two coils. In this case, the net flux linkage will be phi 11 plus phi 12. That means coil 1, that means the first coil has N1 turns and coil 2 has N2 turns. So for first part, that is the phi 1, that is for coil 1, it will have net flux due to the self-induced flux and the mutual induced flux. So whenever there is a linkage of flux and EMF will be induced, that is a voltage. So voltage induced in this coil is given as V1 equals to L di by dt, and similarly in coil 2 V2 equals to M21 di by dt, because in coil 2 there is no self-induced flux. It is due to the flux only found by the mutual inductance of coil 2 with respect to coil 1. You need to remember this notation, it is very important. M21 mutual inductance of coil 2 with respect to coil 1. Now what is mutual inductance? We have learned it before already. Again recall it. It is just the ability of one inductor to induce a voltage across a neighboring inductor. When we change the current in the first coil, this changes the magnetic field in that coil. The magnetic field in the first coil produces a magnetic field in the second coil. Hence, an EMF produced in the second coil causes a current flow in the second coil itself. So, current in the first coil induces a current in the second coil. This is the basic concept about mutual inductance. Again, if we consider the second coil, this time the voltage source is attached to this part. So the coil 2, coil number 2, the net flux linkage to coil number 2 is due to its own flux phi 22 plus due to 1, mutual inductance due to 1, that is phi 21. Similarly, there will be voltage induced, that is V2 equals to L2 di by dt, and hence in case of coil 1 there is no self-inductance. It is Vi equals to M12 di2 by dt. This M12 represents mutual inductance in coil 1 with respect to coil 2. This means mutual inductance in the first coil with respect to second coil is denoted as M12. This is a very important topic, dot convection. Whenever the flux linkage takes place, the current flows, there is a direction of flux, and there happens a lot of things. So by solving numericals, we need some convention. Like in DC circuit, in the Kirchhoff's law, we needed a convention of flow of current, direction. So in this case also, we have to do something like that. Now you can see there are 4 terminals involved. So we can apply the dot convention. The basic fundamental of dot convention is we have to put a dot whenever the current enters or whenever the current exits out of the point. Now, in this case, if a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is positive. I guess this statement is quite difficult to understand. So in simple way, you can see this picture. The current flows through this coil in this direction. There is a mutual inductance, and similarly in the second coil the current flows in this direction. Now we put 2 dots. This current flows, enters into the dot, and the second part also the current flows and enters into the dot. Now when both of the currents are entering into the dot, in that case they are acting similarly. Hence the voltage will be M di by dt. Means this mutual inductance is positive. Clear? Thus the reverse means the negative part. In this part, current is entering through this dot, and the current is flowing in this part and exiting from this dot. Means there are 2 different things. Current is entering through this, current is exiting through this. The entering and exiting part both are different. So we use dot convention. Hence, as these two things are different, we use mutual inductance as negative. V2 equals to minus M di by dt. Similarly, in this case also you can see the current enters through this dot, but in this case, in the second coil, the current exits through this dot. Hence, this is negative mutual inductance. In this case, both the current are exiting from this dot. Both are doing the same thing, so it is positive mutual inductance. V1 equals to M di2 by dt. These are just conventions for numerical use. Now, how energy is generated in a coupled circuit? When two coils are kept nearby each other, there is inductance. It can be self-inductance, it can be mutual inductance, depending upon the circuit. In this case, the self-inductance of the first coil is L1 and the self-inductance of the second coil is L2, and the mutual inductance is given as M. Both the currents are entering and flowing through this dot, means both are doing the same thing, so the mutual inductance will be positive. There is a formula for energy in a coupled circuit, that is, energy stored will be half Li square, as though the things used are inductors. The energy stored in inductor is half Li square, half L1 I1 square plus half L2 I2 square, minus mutual inductance of 1 and Mi into I2. Mutual inductance cannot be greater than geometric mean of self-inductance. You have to remember this every time. The mutual inductance can never be greater than the geometric mean of the self-inductance. This is very useful in numerical part. Now the coefficient of coupling. The coupling coefficient is a measure of magnetic coupling, the intensity with which the magnetic fields couple with each other, that is the first part to second part. The intensity with which they are coupled, that is known as coupling, and that is given by coupling coefficient K. The formula for K is M by root L1 L2, and this M can be further written as K times of geometric mean of L1 and L2. This is a practical application. Energy stored in a coupled circuit. Here we have considered two things. This is iron or ferrite core for maximum linkage of flux. In this case it is loosely coupled, so the coupling coefficient is less than 0.5. In this case it is tightly coupled, the coupling coefficient is greater than 0.5, and in the middle we have coupling coefficient as K equals to 1. This type of devices are used in air core transformers when the core is air, and this type of transformers are generally iron core transformers, in which the core is iron for maximum linkage of flux. Now the more important point, coupling coefficient is depend on four factors. The closeness of the two coils. The more closer are the two coils, there will be more inductance, more mutual inductance among them, more the induced EMF, and hence more induced current. The core. The ferromagnetic core is used for the maximum flux linkage. The more is the flux linkage, more is the induced EMF, and hence more is the induced current. Their orientation. Orientation is very important. Either they are loosely coupled or tightly coupled. That depends on their winding. This winding also decides the coefficient of coupling. So